Welcome to Raw History, where we cut through romanticization and speculation to show you the unfiltered reality of human history. Thermal imaging technology has evolved from military exclusivity to widespread civilian use. Thermal cameras detect infrared radiation emitted by all objects with temperatures above absolute zero, creating images based on heat signatures rather than visible light. Unlike conventional cameras that capture reflected light, thermal imaging visualizes temperature differences, enabling detection through darkness, smoke, and certain materials. The technology operates primarily in two spectral bands: long-wave infrared covering 7 to 14 micrometers and mid-wave infrared spanning 3 to 5 micrometers. These wavelengths correspond to the peak thermal emissions from objects at ambient and human body temperatures, making thermal imaging extraordinarily effective for detecting living creatures against cooler or warmer backgrounds. The physics underlying thermal detection centers on the Stefan-Boltzmann law, which states that all objects radiate energy proportional to the fourth power of their absolute temperature. Human bodies at approximately 37 degrees Celsius emit substantial infrared radiation, creating signatures easily distinguished from typical environmental temperatures. Modern thermal cameras can detect temperature differences as small as 0.01 degrees Celsius, making concealment through temperature matching alone virtually impossible without active thermal management systems. The physics of infrared invisibility comes down to how thermal cameras interpret infrared radiation through three primary components: emitted radiation from the object's surface temperature, reflected radiation from surrounding heat sources, and in some cases transmitted radiation through semi-transparent materials. The computation of temperature from infrared images depends not only on measured radiation, but also on internal camera calibration and the emissivity of the object radiating energy. Emissivity values range from 0, representing a theoretically perfect mirror reflecting all energy, to 1, representing a black body that perfectly absorbs and radiates all energy. Physical objects range from 0.01 to 0.99 on this scale, with highly polished metallic surfaces like copper or aluminum typically below 0.10, while human skin and water measure approximately 0.98. So, this emissivity principle actually creates the foundation for thermal concealment. Materials with low emissivity, they reflect surrounding thermal radiation instead of emitting their own, which can really create confusion in thermal imaging systems. If you're looking at a highly polished metal object with low emissivity, that surface basically acts just like a mirror. Instead of the camera measuring the temperature of the object itself, it actually detects the reflected temperature from surrounding objects. This physical property, it becomes the basis for low-tech thermal concealment strategies that manipulate what thermal cameras actually detect. Heat transfer, in general, occurs through three main mechanisms: conduction, which is direct contact between materials; convection, which is movement through fluids like air or water; and radiation, which happens through electromagnetic waves. Disrupting any of these pathways, honestly, reduces detectable thermal signatures. Insulation blocks conductive transfer, air gaps prevent convective loss, and reflective surfaces redirect radiative emissions. So understanding these principles actually allows for the construction of concealment systems using, readily available materials. Low-tech cloaking really comes down to materials and methods. Emergency thermal blankets made of Mylar foil are probably the most accessible infrared blocking material out there. Engineered with advanced dual-sided aluminized Mylar technology, these thermal blankets maximize both heat retention and reflection, retaining up to 90% of body heat and completely blocking rain, snow, and moisture. The material reflects infrared radiation away from thermal cameras while also trapping body heat underneath. Mylar emergency blankets can reflect up to 90% of infrared radiation, masking heat signatures when they're properly deployed. However, it's important to note, heat does accumulate inside these enclosures, and eventually this creates hotspots that are visible at the edges and openings. So glass provides one of the most effective thermal barriers out there. It's actually entirely opaque to thermal imaging, acting as a complete block to infrared detection. The material's molecular structure absorbs and re-emits thermal radiation right at the wavelengths that thermal cameras detect, which means they only show the glass surface temperature, not whatever's behind it. This property makes windows pretty effective as thermal shields, but, well, it's got limited practical mobility applications. Thick wool blankets, provide temporary concealment mainly through insulation rather than reflection. A thick woolen blanket helps defeat thermal imaging by absorbing and slowing down heat transmission, basically creating a thermal buffer between your body heat and any external detection. The thing is, this material only works for a while. Eventually, heat does permeate the fabric, and that creates a warm signature that's detectable if someone observes you for long enough. Wool's effectiveness really depends on factors like thickness, moisture content, and how long you're being observed. Now, dense netting and ghillie suit materials, they don't actually block thermal signatures, but they do help disperse them. Thick netting is helpful because the holes throughout the webbing disperse the heat signature from thermal warmth detection, breaking up those concentrated heat patterns into more diffuse signatures that are harder to identify at a distance. This technique doesn't provide complete concealment, but it does reduce the recognition range and makes identification a lot less certain. When we talk about strategic concealment and ghost shelters, it's clear that effective thermal concealment requires more than just single material solutions. The construction of a thermal shelter system really combines a few different principles. You've got reflective barriers to redirect thermal emissions, insulating layers that slow down heat transfer, air gaps to prevent conductive pathways, and camouflage patterns to disrupt recognition, even when some thermal signatures remain visible. The concept of a thermal poncho is a good example of this layered approach. By using a military poncho as the base material for structural strength, sandwiching mylar or thermal blanket material between layers, and then adding earth-toned cloth with a bit of ghillie-style camouflage, you end up with both thermal disruption and visual concealment. So, location selection really matters enormously. Positioning yourself near large thermal masses like sun-warmed rocks or even buildings actually allows you to blend in with those existing heat sources. And dense tree canopy is really helpful too. It breaks up thermal signatures from above, especially when there's heavy leaf cover. Plus, you have to consider environmental factors like wind and ambient temperature. Cold environments provide less thermal contrast, making it a bit easier to stay hidden, while warm conditions can actually increase the difficulty of concealment. The principle of standoff distance prevents heat transfer to concealment materials. When thermal protection material contacts the body for extended periods, heat leaks into it, warming the material and allowing thermal signatures to be detected. Suspending reflective materials as overhead tarps with air gaps prevents this conductive transfer while providing protection from aerial detection. Beyond the drone, the future of thermal countermeasures is, honestly, pretty fascinating. Advanced research explores metamaterials and spectrally selective emitters for infrared stealth. Recent studies from 2025 describe near-perfect spectrally selective emitters based on combinations of silicon and hafnium dioxide multilayer films, achieving average emissivities as low as 0.06 in the 3 to 5 micrometer atmospheric window and 0.11 in the 8 to 14 micrometer window. This effectively suppresses infrared radiation while maintaining radiative cooling performance. These materials work through precise engineering of layer thicknesses and refractive indices to manipulate electromagnetic wave interactions at infrared wavelengths. Active thermal concealment systems using thermoelectric devices represent cutting-edge development. Research published in November 2025 demonstrated thermoelectric device-based thermal cloaks that respond within just over 2 seconds, over temperature ranges from about 6 to 109 degrees Celsius. Unlike conventional infrared concealment techniques that rely on emissivity engineering and are limited to specific temperature ranges with response times measured in minutes, active thermal concealment achieves rapid response and broad operational compatibility across both cold and hot environments. These systems actively cool or heat surfaces to match background temperatures rather than just passively blocking thermal emissions. The evolution of thermal detection technology drives parallel advancement in concealment methods. As thermal imaging becomes more sophisticated, incorporating multiple spectral bands and advanced image processing algorithms, simple, reflective barriers prove less effective against sustained observation. The future of thermal concealment lies in understanding detection physics deeply enough to exploit fundamental limitations rather than merely blocking radiation. Human ingenuity keeps adapting, showing that even the most powerful surveillance technologies face inherent physical constraints that informed individuals can leverage. Subscribe to Raw History for evidence-based explorations of detection and concealment technologies that shaped military and survival strategies. And hey, share your thoughts on thermal imaging physics in the comments below.